Good evening, everybody. Welcome to the sequence recommendation session. This is clearly a key session for this conference because in the word cloud this morning, sequence was right in the middle in the biggest letters possible. So this is fundamentally important for the conference. We have 4 presentations, 3 full papers and 1 industry paper. The first paper is entitled Distribution-Based Learnable Filters with Site Information for Sequential Recommendation. Unfortunately, the authors cannot be here to present, but Jai-Kai Tang from Renmin University is going to present on their behalf. So, Jai-Kai, up you come.
So, good afternoon, everyone. The title of my presentation is Distribution-Based Learnable Filters with Site Information for Sequential Recommendation. Thank you for being here today. Sequential recommendation aims to predict a user's next interaction based on their historical interactions. Users often have multifarious interests, leading them to interact with items from multiple categories. Hence, a sequential recommendation requires the modeling of uncertainty, as depicted in the diagram. Consider Jim as an example. He has 2 interests, laptop and backpack. When Jim interacts with the 3rd and 4th items, which belong to different categories, this transition between items exhibits random uncertainty. However, most existing methods rely on a single fixed vector to represent an item, thereby failing to capture the multifarious interests of users and to effectively model the uncertainty in item transitions. In recommendation scenarios, there's a persistent challenge known as a constart. This issue commonly occurs with new users or items that lack sufficient interaction feedback. The limited data availability presents a significant obstacle to recommendation systems, thereby hindering their performance. However, one effective strategy to alleviate this issue is the integration of site information, such as user profiles and item attributes. This additional data can provide a richer context and a deeper understanding of user preference and item characteristics, leading to more accurate and personalized recommendations. Therefore, considering the inclusion of site information becomes crucial. In user sequences, the presence of noise in items is a notable consideration. These noise items characterized by unexpected or irrelevant interactions can impact the accuracy and reliability of user behavior analysis. Handling noise helps in better understanding user behavior and uncovering meaningful patterns. Regrettably, most methods tend to neglect the issue of noise. To address the challenges of uncertainty modeling and the incorporation of site information, we have adopted a novel approach. Instead of using a single fixed vector, which is common in most methods, we represent both items and their associated site information using multidimensional Gaussian distributions. This probabilistic modeling approach allows us to effectively capture and represent uncertainty, leading to more accurate predictions of user behavior, especially in scenarios characterized by high levels of uncertainty. Moreover, we take it a step further by merging site information embeddings with ID embeddings to create the final item representation. This fusion enhances the expressiveness of these embeddings, creating a more comprehensive and powerful representation of items. This comprehensive representation not only captures item characteristics, more effectively, but also enables a precise matching with the user interests. To tackle the challenge of noise inference, we've implemented a solution based on distribution-based learnable filters designed for adaptive noise reduction. Here's how it works. We begin by taking the field's embedding sequence and converting it into a frequency domain data through a one-dimension Fourier transformation. This shift places embeddings into the frequency domain, where noise can be more effectively addressed. Introducing learnable filters is the next crucial step in our noise reduction strategy. These filters selectively attenuate undesirable noise components within the embeddings while preserving essential information, making sure that the embeddings remain both informative and reliable. We then resolve this process through an inverse Fourier transform to revert to the time domain representation, facilitating subsequent operations. This approach achieves adaptive noise reduction, enhancing overall system robustness. Moreover, maintaining a consistent item representation structure is crucial during both the model training process and the prediction. Specifically, since the inferred item representation is a fusion of ID embeddings and site information embeddings, the positive and negative items involved in the training process should utilize the fused item representation rather than relying solely on pure ID embeddings. Similarly, candidate items should also employ the fused item representation, neglecting structure consistency in representation will introduce biases into embeddings, thereby affecting the model's performance. Here's the architecture of our proposed model, which consists of the embedding layer, stacked the learnable filter layers, and the prediction layer. Within the embedding layer, we represent both items and set information using Gaussian distributions and subsequently fuse their representations. The fused embedding sequence is then passed through L-stacked learnable filter layers to reduce noise. This process generates inferred item representations used for predicting the next item in the sequence. For more details, please refer to our research paper. Next, comes to our experimental section. For our experiments, we chose 4 public available real-world datasets from Amazon review datasets to ensure data quality. We filtered filtered users and items with fewer than 5 interactions. The table displays dataset statistics after pre-processing, including the quantity of item categories and brands, as we utilize them as set information. We chose 8 recent models used in sequential recommendation tasks as our baselines for comparison. To ensure fair comparison, we also included methods that incorporate set information, such as S3REC and DRFSR. For further details regarding our experimental setup, please refer to our research paper. In our comparative experiments, evaluating model performance on the entire item set would be time-consuming, as we adopted a grid search for optimal parameters. Therefore, we used the candidate set consisting of 1 positive sample and 99 random negative samples. Models that incorporate set information, which contain DLFS-REC, S3REC, and DIFSR, outperform those that do not. This is because that information provides valuable additional data to express the user interests. Among models that do not incorporate set information, FMLP-REC with learnable filters achieved the best performance. underscoring the effectiveness of learnable filters in sequential recommendation. As the results show, our model achieved the best performance across all metrics and datasets. Gaussian embeddings, set information incorporation, stacked learnable filters, and the FLLP component are all crucial components of our model. Our ablation experiments have clearly demonstrated that the removal of any of these components results in a substantial drop in performance, indicating the significance of each part. In the hyperparameter sensitivity experiment, we explored the critical hyperparameters for DRFS rec, including hidden size, the number of filter layers, and the hyperparameter. We found that DRFS rec excelled with a hidden size of 128, but performance declined with size too small or too large. Similarly, increasing filter layers initially improved the model, but hurt performance once a certain threshold was surpassed. Setting hyperparameter lambda to 0 significantly worsens the results, highlighting the importance of considering positive and negative atom distances. In summary, optimizing these hyperparameters is crucial for achieving the optimal model performance. Set information plays a crucial role in comprehending user preferences and significantly contributes to the outstanding performance of our model. As a result, we integrate various types of SI into set information into DRFS rec to explore their efforts on the overall performance. And then we use TSNE to visualize atom embeddings learned by DRFS rec and find that the inferred atom exhibits a similar shape and a large overlapping area with the ground truth atom. This indicates a close match between the inferred atom and the ground truth atom. However, without set information, the inferred atom and the ground truth atom have no overlapped area and exhibit significant differences in shape, indicating their dissimilarity. Besides, the atom embeddings in DRFS rec have a smaller shape. These results demonstrate that incorporating set information helps capture user interests and reduces uncertainty in atom representations. To verify the effectiveness of DRFS rec in elevating the cold start issues, we report separate performance evaluations for different user and item groups. For cold start user scenarios, among the group with the shortest sequence length, DRFS rec achieves the largest improvement when compared to other models across all different datasets. This suggests that our model effectively mitigates the user cold start issue. Additionally, as sequence length increases, the relative improvement diminishes. This happens because longer sequences naturally contain more historical data. Models can use this extensive history to better comprehend user preferences. Consequently, the influence of set information becomes less pronounced in such situations. As depicted in the diagram, each model shows better performance as the popularity of items increases. This indicates that predicting frequently interacted items is relatively straightforward in a recommendation task, while predicting unpopular items remains challenging. Compared to other models, DRFS rec demonstrates marginal improvements in predicting high-frequency items, but it shows remarkable enhancement in predicting unpopular items across all datasets. In summary, based on the experimental results, our model effectively elevates the cold start problem, whether it's for user cold start or item cold start scenarios. We believe that incorporating set information to augment item representation and leveraging the fused representations for loose computation and item prediction can be applied to various other models, resulting in enhanced performance. As our results indicate, the incorporation of set information significantly boosts the performance of GRU4-REC, SAS-REC, and FMRP-REC. However, despite this, our model still outperforms these approaches. This suggests that the success of our model is not solely attributed to the integration of set information, but also relies on the rationality of its components and the superiority of its structure. In our work, the utilization of fused Gaussian embeddings to represent items not only enhances the expressiveness of item embeddings, but also enables effective modeling of uncertainty. Additionally, the distribution-based learnable filters work adaptively to attenuate noise. We have extensively validated the effectiveness and the superiority of our method through experiments conducted on 4 datasets. And finally, my presentation ends here. Thank you all for your time and attention. That's all.
Thank you, JK, for presenting the work of our friends back in China. So what we have is the author is on Slido, but if you have a question in the room, JK will try and answer it. Are there any questions?
And if you have some questions, you'd better to ask in the live platform.
Yeah, sure. But if there are any, I mean, so I was wondering, just on slide 16, could you go back to slide 16? I wanted to understand what the different graphs were. Can you go back to slide 16?
Okay.
No. Slide 16. Go back.
Oh, close it.
Slide 16. I want to ask a question about a slide. You can't answer a question about the graphs, no? Okay. Thank you, JK, for presenting that. The next paper is entitled Reciprocal Sequential Recommendation. This is a paper by Renmin University and Boss Ziepen, and Xiaolei Wang is going to be presenting this paper. Xiaolei.